In this video, I'm going to talk about fusion of stars. Like always, I'll start with a bit of theory, and then I'll show you some worked examples. Please take a moment to read the success criteria I plan to cover. So let's just remind ourselves what kind of conditions we need for fusion to take place. It can't just happen anywhere. First, it is the process of combining two smaller nuclei to create one larger nuclei. Now, I've seen lots of different definitions here, and I would suggest that the word nuclei needs to be used, not particle, not atom. It's actually the nuclei that needs to come together. Now, nuclei have a positive charge, so it's not like they're going to want to get together and create one larger nuclei. So the first thing we're going to need is a very high temperature. And what will that give us? Well, it means that the particles will have a lot of kinetic energy, and that will be used to overcome that positive forces of repulsion. Now you might say, why did I use the word particles here after I just said don't use it in this part? Well, that's because in this section, I'm more interested in the fact that they have to have a lot of energy to come together. So I can be a little bit more general here. But the actual pieces that fuse are the nuclei. So we've got this electrostatic repulsion, sometimes called the Coulomb force. But we need a little bit more. The reason being, just because two nuclei hit each other doesn't necessarily mean it's going to cause a reaction. So I really also need a high pressure or density. And what is that trying to tell us? Well, it means that the nuclei are going to be close together. And this will increase the frequency of collisions. Now I know I called it just fusion, and here I'm going to be a little bit more specific again. We're going to call it a proton-proton cycle, or hydrogen burning, using up hydrogen in our reaction. I'm going to go through as a three-step process to show how we go from just having hydrogens to actually making helium. Now overall, I'm going to start with 4 hydrogen nuclei. Again, notice the word nuclei. That means I only have protons, and hydrogen only has 1 proton, so its hydrogen nuclei is just a proton. And then I'm going to end up getting 2 beta particles and some helium and some neutrinos. As with all fusion reactions, we're also going to have energy released all the time. I know some textbooks may or may not have this, but I actually think it's a really good thing for us to go through. The reason being is this is going to remind us about different things we've already done in this topic, in this theme in IB. We need to know about things like beta particles. We need to know about binding energy, and this process is going to actually combine all these things together. Okay, so this red circle here is to be my proton. You can see I have 2 of them together, and they have to come in contact, as we said, and we're going to make sure that there's enough energy for them to fuse together. But we're not done there. We need them to stay together long enough for one of them to go from being a proton, and this one has actually had a beta positive decay, giving off beta positive, which remember is an antiparticle, so it's also going to make a neutrino. A beta minus will make an antineutrino. I've written here a positron. Remember, that's the same thing. A positron is the same thing as a beta positive particle. And now what I have here is a neutron. This takes a long time. It has a slow reaction rate. But in the process of giving off the beta and the neutrino, I also now have given off some energy, 1.4 mega electron volts. You don't need to know these exact numbers, but I've got them along here just to show how they add up. Okay, so this is what I have from the last time. This is my proton, this is my neutron, also called a deuterium nuclei. Remember, deuterium is 2, 1 hydrogen. It has a nucleon number of 2. That means there's 1 proton, 1 neutron. I need it to combine with another proton, and notice now I've got 2 protons, 1 neutron. This is going to be my helium-3 nuclei. This also is a very fast reaction rate. And take a look. Another 5.5 mega electron volts are going to be given off when we have this reaction. Well, it's a good thing that step 2 happens very quickly, because notice I need 2 of these helium-3 nuclei to come together. But when they come together, 1 proton is going to pop off either side. So notice 4 nucleons, 4, 2 helium, and here's 2 protons. I also get some more energy when this happens. So let's go through our net reaction. We had 2 protons come together. They're going to stay long enough for one of them to turn into a neutron, giving off a beta positive and a neutrino. I'm going to get another pair doing the same thing. Step 3 means I'm going to get those to come together. They'll give off 2 more protons. They'll go on to be part of new reactions. And we've got our 2 beta then and 2 neutrino. In total, if you were adding all that up, I got 26.7 mega electron volts for each reaction. Now, I don't want to dwell on this too much, because I do think this goes a little bit beyond. But there are other processes possible. I'm just showing you the proton-proton cycle because I think it's the basis. It's going to be happening in our main sequence stars, but some of the larger ones can then have additional ways to make other elements. Well, with all of this fusion going on, how do the stars stay stable? Well, what we were just looking at was a lot of reactions happening here in the core, and it's going to cause a radiation pressure as it releases energy, as well as the fact that all these particles have a high temperature, and we said that was good. It had a lot of kinetic energy. Together, they will combine an outwards pressure, both radiation pressure and thermal pressure. So why does it not just blow up? Well, we also have the force due to gravity that's attracting all of these particles together. And it's these 2 pressures that are going to balance and create our stable star. So let's go through an example. The sun releases energy at the rate of 3.9 times 10 to the 26 watts through the fusion of protons to create a helium nuclei. Well, obviously we've got a lot of them going on. Why does the fusion of protons produce energy? And remember I said this is why these questions are important. They tie in pieces we've had from before. What they're looking for is this idea of binding energy. When 2 protons come together, the resultant mass is less. We call this the mass defect. What happened to it? No poof, Harry Potter magic. Well, the mass was converted into energy. Remember, E equals mc squared, and this is the binding energy. Remember, binding energy is not the amount of energy holding the nucleus together. It's the amount that's given off when the mass decreases. Or you can think about the amount of energy needed to separate the nucleus into its separate nucleons. Okay, part B. Calculate the number of fusion reactions in 1 second if each one releases 26 mega electron volts of energy. Now, it wants to know about the amount each second, and that's where I say, remember what a watt is. That is actually a joule per second. That means watts is the amount of energy per second. So if I take the total energy per second, that's the watts, and I divide that by 1 reaction, that's going to give me 3.9 times 10 to the 26 all over 26 mega electron volts. Okay, now we got to change that because this is in joules. So mega electron volts, I'm going to have to go times 10 to the 6 to get rid of the mega. And to go from electron volts to joules, I need to multiply by 1.6 times 10 to the minus 19. Now, when I pick up my handy dandy calculator, 9.4 times 10 to the power 37. And this would be the number of reactions per second. Because notice this divide by second here. So I could also then just say it's 9.4 times 10 to 37 reactions in 1 second. Okay, example number 2. We have these protons in a star where the temperature is greater than about 10 to the power 7 Kelvin. It takes the fusion of 4 protons to form that helium nucleus, and this is known as the proton-proton cycle. The net energy released in a single helium nucleus is a very small number. Calculate the binding energy per nucleon of the helium-4 nucleus in electron volts. Okay, so our total binding energy was 4.53 times 10 to the minus 12. That's in joules. And there are 4 nucleons. They're making sure you know what the term nucleon means. And if I pick up my handy dandy calculator, I get 1.13 times 10 to minus 12 joules. But I need to turn that into electron volts. So we know that 1 electron volt is the same as 1.6 times 10 to the minus 19 joules. And that's going to give me 7.1 times 10 to the power 6 electron volts when I pick up my handy dandy calculator. Part B. The fusion of the helium nuclei to make heavier elements occurs the red giants, above the value 10 to the power 8. Explain why fusion of helium requires higher temperatures than the fusion of hydrogen. Well, if you remember why we needed to have that high temperature is we needed to have high amounts of kinetic energy to overcome the Coulomb force, the electrostatic force of repulsion. What's different about helium? It has a higher charge on its nucleus. Higher temperature is going to give us a greater amount of kinetic energy to actually get them together. And finally, part C. Describe how this hotter star can still be stable. Outwards pressures due to temperature and radiation is balanced by greater inward pressure of gravity. And that could be more particles and closer together. Well, I hope that's helped you. Please read through the success criteria one more time, and hopefully you can say yes to all these points.